Hi, good morning, everyone. Today I'm going to walk you through a Psych 292 tutorial on hypothesis testing, p-tests, z-tests, and we'll bring it all together just to talk about what it means. My name is Bobby, and I'm a fourth-year psychology and math student here at Waterloo. So in this tutorial, we're going to focus on t-tests. We'll introduce the essential concepts as we walk through a practical example. And while most of the focus of this tutorial will be on statistics, we'll also look at how we can perform these calculations in a statistical programming language called R. R is a great language for any kind of research or just performing any kind of stats. It's used a lot in psychology research. You can kind of think of it as SPSS on steroids. So I'm going to be using this little heading called using R throughout the tutorial to denote any kind of optional information about the R programming language. So my intention is, we'll focus mainly on the actual concepts, but we'll also do some calculations. And we'll use R as a little bit of a way to help us with those calculations sometimes. So in this tutorial, like I said, we're going to be looking at t-tests. And ideally, you'll have just learned t-tests in Psych 292 by the time you're watching this. I've created just a fictional data set for this tutorial. Hopefully it'll be interesting enough and engaging enough for everyone to be able to follow along well. And we'll run some stats on that. So we'll be conducting t-tests on a data set of 18 participants. These example data describe the experiences of our 18 participants in an experiment about music genres and well-being. Now, this is just a fabricated experimental procedure, but it's a bit of a story that will hopefully help everyone understand what these data mean. So we randomly asked 18 students in our Psych 292 class to participate in this study. Each participant in the experiment began by reporting their baseline initial well-being score. And then well-being was operationalized as a self-report measure, their perceived health and happiness. Participants rated their well-being on a score of 1, which is a very low well-being, to 7, a very high well-being. Participants were also asked to report the number of coffees that they drink on an average day, because we think that coffee consumption might be a predictor of one's well-being. In real life, it's probably not. We don't know. After we measure our baseline well-being score and asked about the coffee consumption, we began the experimental manipulation. The independent variable, which is the one we're manipulating, is music genre, because we randomly assigned each participant to one of 3 music genre conditions. We either put them in a classical music condition, a blues condition, or just a control condition. In the classical music genre condition, the participants were asked to listen to 15 minutes of classical music when they first wake up for the first week, or for 1 week. Likewise, in the blues music condition, the participants were asked to listen to 15 minutes of blues music when they first wake up for that same 1 week. In the controlled condition, participants were not asked to listen to any kind of music for the week. I should note that this is concurrent, so all 3 conditions are happening during the same week of the term, ideally. At the end of the week, we measured, in a post-test, the well-being of each participant again, using the same 1 to 7 self-report measure that I described above. So this is ideally just to get a sense of any potential change in well-being throughout that week. Now, recall that this is an experiment because we're manipulating our independent variable, which is music genre, and randomly assigning participants to conditions, which are the levels of the independent variables. To make sure you're clear on all of these terms, I would suggest going back to review your Psych 291 notes from last term. Now, we're going to have a look here in a minute at our data set. But just to summarize everything, the independent variable in the data set is music genre, which is either classical, blues, or control. The dependent variable, is the self-report well-being, measured on a scale of 1 to 7. We're also controlling for coffee consumption. Now, the data set. Like I mentioned, I'm going to be including a little bit of our code, but this code is really not meant to overwhelm people. It's just there if you're genuinely interested, and you should be just fine in this tutorial by completely ignoring the R code. The R code is meant to supplement and expand your knowledge, but you should be able to get just as good an understanding of t-tests by just completely ignoring the R code. Like I said, the focus of this tutorial is t-tests, hypothesis testing, and z-scores. So if you're getting bogged down by the R code, just ignore it, don't worry. Now, using R. To load a data file in R, we can use the following code. And this is just for informational purposes. In R, like other programming languages, or even just like math, we can assign values to variables, just like you would in your research. In this case, we're assigning the contents of the data file on my computer, called well-being intervention data, to a variable called the same thing, well-being intervention data, using the assignment operator, which is this little arrow. This is to say that we're taking this data file and assigning it to this variable. Now, what is this variable? To most people, it just looks like well-being underscore intervention data. But it's really just a spreadsheet, essentially, a table of the data that we have. So we can actually display this. In R, if we just type in the name of a variable, that'll actually show us that exact variable. And like I said, in this case, well-being intervention data, that variable is a table. So if I display it by typing it in here, like I already have, it'll show us this beautiful table, which has all of the variables that we've already been talking about. It has the participant ID, which is something I guess you would be familiar with if you've ever done a SONA study or something like that. You would have a SONA ID. This is just to uniquely identify each participant in the study. We also have the coffees variable. This is what we asked the participants at the beginning of the week. How many coffees do you drink per day? We also have the music condition that they were assigned to. Some people were assigned to the control condition, others were assigned to the blues condition, and finally, people were randomly assigned to the classical music condition. Now, at baseline, that is, at the beginning of the week, we gathered their self-reported well-being score on a scale of 1 to 7. Likewise, at the end of the week, people reported their well-being again, after going through their assigned intervention. This table is really just meant to help illustrate the data. And this is exactly like what you would get in a test question, for example, if you were to have to compute some statistics. So I have a couple pages here. That's just because we have more than 10 rows. We actually have 18 rows because we have 18 participants. So these are the first 10 participants. We also just have these other 8 participants, make up the entire 18 participants that were included in this study. So, as with any kind of research, we would have some research questions. What are some research questions we might want to answer? Well, does blues music cause university students to experience different levels of well-being than classical music? We're not sure yet. Does 1 week of classical music lead to greater reported well-being? Well, we need to note that lead to is another way to make a causal claim. And recall from your Psych 291 that we can make a causal claim in an experiment, because experimental research abides by the 3 rules we need for causal claims. If you're unsure why this means we can make a causal claim, I'd suggest you look back at your Psych 291 notes. Well, to answer these questions, we can use hypothesis testing. Put simply, hypothesis testing is a way to test whether the hypothesis we make about a population is true or false. The only way to prove for certain that different music genres lead to different levels of well-being in the population would be to experiment with every university student in the world, the entire population. But it's not exactly reasonable for us to do that. So we kind of have to settle for a best guess about what the sample data are telling us about the population. And this should be a concept you're generally fairly familiar with already. So doing this kind of research where we make inferences about the population from the sample requires a new type of statistic. And it's a very powerful one. Before, we had to settle for descriptions of our sample. What is the mean, the median, the standard deviation? These are called descriptive statistics because they describe the sample data exactly. For example, in our dataset above, the average number of coffee that participants reportedly drink per day is exactly, or at least rounded to, 2.389. So that's an exact number, an exact description of this sample. The number of participants in this experiment and in this sample are 18. These statistics exactly describe aspects of our sample. So in R, we can use R, for example, to find the well-being mean for the participants before and after treatment of classical music. And we can do this by taking a subset of that well-being table above. If we just look at the musical participants, the participants in the classical music condition, we can actually create a new variable by assigning this subset to classical participants. Then we can use a function called mean in R, which is just to simply take the mean of a list of data, which is exactly what you would do by hand. You would add it all up. You would divide by n. This gives us a new variable that I assign to classical baseline well-being, because this is the baseline well-being average. We also have classical post well-being. This is the post-test. We can even print the results for everyone to see, like follows. So I can use this print command here, and then we end up with this, a nice little description saying before the intervention, the classical condition reported an average well-being of 4.5. After the intervention, the sample participants reported an average well-being of 5.5. So this shows us that well-being is higher on average in our sample after the week-long intervention for the classical group. But does this mean that we have enough information to confirm that our second research question is true? So does 1 week of classical music lead to greater reported well-being? Well, we don't know that yet. We don't have enough information. In the case of hypothesis testing, we can look at our sample and say for certain that, yes, 1 week of listening to classical music leads to greater well-being in the population. We can't do this for certain, because there's no way to know about the population for certain just based on our sample. Any sample has sampling error. We're also moving away from descriptive statistics with this research question, because we're no longer looking at ways to describe our sample. We're looking at ways to infer conclusions from the sample about what the population is. So we need to test our hypothesis using something called inferential statistics. These are inferences we make about the population using our sample. These statistics are no longer facts per se. They're guesses about what our sample is saying based on probability. So the hypothesis. When we're testing our hypothesis, we talk about the null hypothesis and the alternative hypothesis. Ideally, you've already seen these hypotheses before. The null hypothesis, written H0, is the hypothesis that this difference does not exist between groups. We might say that one group is equivalent to the other. In our example, the null hypothesis is that there's no difference in well-being between baseline and after the classical music intervention. The alternative hypothesis, written H1, is the hypothesis that there is a difference. So we might say that one group is not equivalent to the other group. In our example, the alternative hypothesis is that there is a population difference in well-being between baseline and after the classical music intervention. Well, we're starting to work our way toward this new concept of the t-statistic. So, as a motivating question, how do we know if there's a difference between two groups? You might be wondering if we can just simply compare the sample means of both groups and see if they're the same or not. But this doesn't really work. For our example, the null hypothesis is that no population difference in well-being between baseline and post-classical music intervention exists. H1 is that there is a difference between baseline and post. So we know that the average well-being of the sample before the classical music intervention was 4.5, the pretest. We also know that after a week of classical music, the mean well-being was found to be 5.5. We can see that the two are different by 1, so we know for a fact that the means in the sample are different. But that's not really what we're asking. We're asking if these means are different in the population. This is a trickier question, because we didn't survey the entire population of students, of course. So, remember the z-score? Z is a great way to figure out how far the population mean is from a value in terms of standard deviations. So, for example, if we knew the all-time average December morning in Waterloo, -3 degrees Celsius, that is, if we knew that mu is -3 with a standard deviation of sigma equals 1, and we measured that the morning of December the 4th was -8 degrees, x equals -8 in Waterloo, well, we could calculate a z-score as follows. Because z is x minus mu divided by sigma. So that is the difference between a score and population mean divided by the population standard deviation. So -8 is that one score we measured. -3 is the population mean. And then we divide by 1, which is the population standard deviation. We get -5. So what this z-score is really telling us is that the morning of December 4th is actually 5 standard deviations below the average population temperature. Remember that we could look at our z-table at a 0.05%, or sorry, just 0.05 significance, and see that only less than 0.00004% of days are expected to be below this level. So -5 standard deviations below the mean is significantly below average given our standard deviation. That's pretty cold. We can also use z-scores to compare different samples when we're given the population standard deviation. If a sample of 30 people from before the classical music intervention had an average well-being score of 2, that is, if their mu1, which is just notation for the pretest, is 2, and if the sample people after the classical music intervention had an average well-being score of 4, we could calculate the z-score. Of course, we need to know the standard deviation. If we are given the population standard deviations, then we're good to go. In this case, let's say that we're given 1.5 for the pretest population standard deviation and 1 for the post-test. Well, we need to calculate our standard error. And again, ideally, this is something you've done before. So we do this as follows. And we achieve 0.32914. So we can use this standard error to calculate our z-score, which is the difference between groups. So we take our 4, which is the post-test, and our 2, which is the pretest. And we find that there's been a change of 2. We divide that by our standard error. We find 6.08. So we end up with this z-score of 6.08. Remember that we're testing our null hypothesis, that the two groups are the same. So this means that we would expect no difference. If there were no difference between the groups, we would expect there to be a pretty close to 0 standard deviation difference between them. But we found a difference of over 6. If we search up the z-value in a z-table, like I put in here below, we can see that this z-value is actually above the 99.99% all possible z-values. So again, we would look up our z-value using the column here. 6.08, these are all less than 1, so moving on to page 2, these are all between 1 and 2. And we still don't have a high enough z-value yet. So this is actually the last value that our table reports, if our z is 4.9. If our z is 4.9, then this is actually the percentage. So a z of 6.08 is surely much higher. Therefore, this z-value is much above 99.999% of all possible z-values. So it's a crazy outlier. Remember that we only need to be above the 97.5% mark to say that p is less than 0.05 and to reject the null hypothesis. Well, we're well past it, so we can reject H0. We say that there's a significant difference between the two groups. Our classical music intervention worked. So z-scores are great, but we've actually just encountered a limitation to z-scores here. What's wrong with the z-score? Well, nothing's wrong with the z-score, but it has its limits. The z-score can only be used if we know the population standard deviation, sigma. In the example above, we had to be told that the first group had a population standard deviation of sigma 1 equals 1.5, and that the second group had a population standard deviation of sigma 2 equals 1. In the context of our problem, if I were to ask you what the average number of coffees a Psych 292 student drinks per day, what would you say? How would you measure it? Well, being the astute Psych student that you are, you would probably gather a sample of Psych 292 students, ask them about their coffee drinking habits, find the mean, standard deviation, and be on your way. Well, that's the right way to calculate the sample statistics. But it's not the same as the population standard deviation, because in order to calculate the population standard deviation, again, we would need to find the average number of coffees that all Psych 292 students at Waterloo, and in the world for that matter, drink. So this isn't really a realistic endeavor. And this is why it's hard to actually gain access to those population statistics. This is where the t-statistic comes into play. So the z-score lets us decide how different two samples are when we know the standard deviations of the populations. But as discussed above with the coffees, this isn't always very practical. Usually we don't know anything about the population. We only really have our samples usually. In these cases, instead of a z-score, we use a t-statistic. The major difference between the two statistics is that z-scores requires to know the population standard deviation, whereas t-statistics only requires to know the sample standard deviation, which is much easier to calculate because you could just go around to your Psych 292 class right now and ask each person how much coffee they drink, and then take the standard deviation. Well, we now can use the sample statistics to estimate the population within a margin of error, which is our p-value. There are a few different types of t-statistics, but they all involve calculating the difference between two values over some measure of spread, just like a z-score does. Like I said, there are a couple different types of t-statistics, but there are two main cases. First one is dependent. So dependent t-tests, which are also sometimes called pair t-tests or groups or paired groups, just variations of those names. This is the one that is most familiar to what we are doing above with the pre and post test classical music groups. Only now we don't need to be given the population standard deviations because t-tests kindly let us use our sample standard deviations. This type of t-test is called a dependent t-test because we're looking at the differences within the same group of people, just over time or over some intervention. So just as a z-test looks like this, where we take the difference between our means and divide by essentially an average of our standard deviations, population standard deviations, called the standard error. A dependent t-test is pretty much exactly the same thing. It's just that we now use our sample estimates of the means and standard deviations. So it's honestly the same thing. We just do something different with the table when we look it up. We no longer use a z table, we use a t table. To repeat, a t-test is still calculating the number of standard deviations between scores. It just does so using a couple more estimates than what we did before, whereas before we were pretty certain. So let's say we have the exact same sample as our last example. The 30 people before the classical music intervention had an average well-being score of 2 and had an average well-being score of 4 after the intervention. The only difference this time is that we're not given the population standard deviations. That's the only difference. And this is the only reason why we use a t-test. So let's assume that we had all the raw data, so we were able to find the standard deviations of each sample. Let's say the pre-test sample standard deviation is 1.5 and the post-test is 1. So these are the exact same numbers as above. It's just that now these are sample statistics instead of population statistics. They're estimates. So not surprisingly, when we calculate our t-value, it's actually exactly the same. Because of course, we're doing 4 minus 2 divided by our 0.329, which is of course the 6.08. Only difference is before we found z equals 6.08, and now we found t equals 6.08. So what's the big difference? Well, when we calculate sample standard deviations, we're taking a bit of a guess, because a sample will obviously not give us the exact standard deviation of the distribution. So really, using a t-statistic introduces a bit more error than the z-statistic does, because we're estimating a bit more of the problem. Whereas before, we were given exact numbers. We were making less estimates. Well, the benefit of the t-statistic is that it actually accounts for this extra error, this extra risk, this extra guess, with something called degrees of freedom. Degrees of freedom is a simple way to account for the added error that's induced by using estimated values in place of a true value. So in this case, we're using estimated sample standard deviations in place of a true population standard deviation. So we need to take the problem's degrees of freedom into account. The biggest issue with using an estimate is that we're only using a sample number of people. So not every person in the entire universe, like the population does. But having a small n like this, we're taking on a greater risk that the sample standard deviation isn't 100% accurate. In fact, the smaller the n, the greater the chance of error there is. And this is kind of intuitive too, because if we took the well-being scores of 1,000 Psych 292 students, we'd have a better idea of what the mean and standard deviation of the population might look like than if I only look at the well-being of 5 Psych 292 students. That's not very representative. Well, degrees of freedom take this sample size into account because degrees of freedom is actually defined as follows. Degrees of freedom is the n minus 1. So degrees of freedom is actually a direct function of the number of people in the sample. So using degrees of freedom, we're now able to actually consider the sample size in our statistical decision-making process. Let's introduce the t-table. Just like the z-table, I've made a little table here where we have all of the different p-values that we might need at the 0.05 p level. Well, the t-table functions a little bit differently than the z-table. when we use the z-table, we find the percentile of the standard normal distribution by using a specific number of standard deviations. So if, like the above, we were trying to look up that z equals 6.08, well, we would use this leftmost column to find the 6.08 mark, and we would find a percentage here. This shows us what percentage of the distribution lies below that z-score. And of course, we would only need a 97.5% of the scores lying below to show that p is less than 0.05. That we can reject the null hypothesis. Well, in the case of our t-table, we don't actually use our t-value to look up the percentage. We actually use our degrees of freedom. And this goes back to the whole considering the error concept. In this example, we have a sample of size n equals 30 people. So this means that our degrees of freedom is actually df equals n minus 1 equals 30 minus 1, which is 29. Looking this value up in the table, we find a significance threshold of, here's 29, e equals 1.699. So what does this mean? Well, this means that we would need to observe a t-value of 1.699 or more in order to say that 97.5% of the population lies below this mark in the z-distribution. In that way, we can reject our null hypothesis. So as long as our t is greater than 1.699, we found an effect that is significant at the p less than 0.05 level, enough to comfortably reject the null hypothesis. Since our t equals 6.08, we reject the null hypothesis. P is less than 0.05. So to tie this back to our original question, we had the following null and alternative hypotheses. H0 is that no population difference in well-being between the baseline and post-classical music intervention existed. H1 is that there is a population difference in well-being between baseline and post-classical music intervention. Well, we have enough stats knowledge now to figure this out. Better still, we can try to use the R programming language to solve this. We'll do it both ways. We need to calculate the mean and standard deviation of Psych 292 students' well-being before the classical music intervention. So we'll display this data once more. We'll also use it to calculate some statistics. In this case, we've taken our total table of data, which is the well-being intervention data, and we've done this thing where we filter so that we only look at the participants whose music value equals classical. In this way, we've effectively only selected the 6 participants that are in the classical music condition. So using this data table, as shown above, we can calculate some descriptive statistics that we'll need. So we can calculate our n classical, which is the number of participants, obviously 6. We can calculate the mean of the pretest value by looking only at the baseline well-being column. And we can calculate the standard deviation using the SD of that column, standard deviation. We can also look at the mean of the post-test and the standard deviation of the post-test in the same way. We can also print these values. So again, remember that we've assigned these statistics to new variables now. So we have n classical to represent the number of participants in that condition. We also have m pretest and SD pretest. And then finally, we have m and SD post-test to represent the mean and standard deviation of the post-test. So we can print these values out using R. If we go print n classical, we get 6 because that's the number of participants. If we go print m pretest, we get 4.5 because that is the average of 4 plus 5 plus 4 plus 5 plus 5 plus 4. We also can print our standard deviation of the pretest, which is 0.55. We can also print the mean post-test and the standard deviation of post-test. So finally now, using R, we can calculate our degrees of freedom. And this really isn't a difficult thing because degrees of freedom is assigned to be n, classical, minus 1. And we'll print it, 5. Minus 1 is 5. Okay, well, we just used R to find n equals 6, m1 equals 4.5, m2 equals 5.5, SD1 is 0.55, SD2 is 1.05, and df equals 5. So we now have all the information we need to do some arithmetic. So let's calculate our t-statistic using these stats. Well, since we're looking at a dependent sample, we can use the formula that we found above and input our values. Post-test well-being was 5.5, pre-test well-being was 4.5. So we subtract those, get 1. And now we essentially, again, we take the standard error, which is essentially an average, weighted average almost, of the standard deviations. We get 0.483. Well, this gives us a t-value of 2.07. So that's great. We've just done that by hand. And you can do this by hand too, using the table above. Well, we can also use R to calculate this t-statistic as well. So we're going to assign to a variable t the difference between mean post-test and mean pre-test, which is exactly this 5.5 minus 4.5 above. And then we divide by the square root, just like we've done here, of the pre-test standard deviation squared and the post-test standard deviation squared divided by our n, which is 6. And if we print this t, we find miraculously that we find the exact same value, 2.07. Although here it just has a few more decimal places, 2.070197. So we get the same value just a whole lot quicker using R. Therefore, we find t equals 2.07 with df equals 5. Let's look this value up in the t-table. Well, in the t-table, again, we search by degrees of freedom. So if we go to 5 degrees of freedom, we find that we would need a t-value of 2.015 or more in order to reject the null hypothesis. Well, we have t equals 2.07. So the t-value we calculated actually meets and surpasses this level, so we can reject the null hypothesis. That is, there is a significant chance that there is a difference between the pre-test and post-test well-being samples. In other words, the classical music intervention appears to have worked. That being said, we're only using n equals 6 participants. Notice that the more participants we use, the lower the calculated t-value needs to be to reject the null hypothesis. For example, if we were to use 10 participants, we would only need a t-value of 1.81 instead of 2.01. As discussed above, this actually makes sense because the larger our sample is, the more we can believe that those standard deviations approach the real deal, population standard deviations. In APA 7 format, we might be able to report this finding as follows. A significant change in self-report well-being was measured within the n equals 6 participants between pre-test and post-test, 7 days later. P of 5, which is the degrees of freedom, equals 2.07, meaning that P is less than 0.05. So it's significant. Well, I mentioned that there are 2 main types of t-tests that we'll concern ourselves with, and we just looked at the first one, which is the dependent one. We're now going to end the tutorial by looking at the second major type of t-test we can perform. This is called an independent samples t-test. This t-test is only slightly different from the above one, because instead of looking at within participant change across time or across intervention, we look at whether 2 different or independent groups of participants experience significant differences This type of question is useful if we were to investigate whether the change that is experienced in the classical condition participants over time is greater than the change that is naturally experienced in the control condition over time. So from an experimental standpoint, this is really helpful to help rule out maturation effects or history effects that were previously left uncontrolled with our above dependency test. Because if you don't consider changes in the control group and only focus in on changes in one of the experimental groups, as we did above, we're leaving these maturation and history effects uncontrolled. That is to say, we're not checking to see whether there's just a natural increase in well-being across the week. This aspect of control is one of the beautiful features of an experiment. Really, there are only two differences between the dependent and independent samples T. First, by design, two independent samples have a chance to be of different sample sizes, different n's. Therefore, instead of just referring to n in our t-statistic formula, we must consider the possibility of n1 and n2. Essentially, n1 is just the sample size of the first group, n2 is the sample size of the second group. These could be the same or they could be different. The second difference is that since we're now considering n1 plus n2 participants in total instead of only n participants, we must use a different value for our degrees of freedom. Well, we have two different values here. So our degrees of freedom is actually going to be this first n minus 1, as well as the second n minus 1. So n1 minus 1 plus n2 minus 1. That'll be our new degrees of freedom for independent samples. It's almost the same thing. So we can then go about calculating our t the same as before, and we'll do just that. Recall that we already have all the values for the classical music condition, and we'll just use R to print these values out just one more time. So we found previously our n classical, our m pretest, our standard deviation pretest, our m post-test, and standard deviation post-test. Now, we'll use the exact same method above to calculate the control descriptives. So again, we're taking our entire data set and we're filtering it by only the control music participants, the ones who didn't receive any music throughout the week. So we're going to calculate some descriptive statistics on this table, just as we did above. We calculate n control, which is the number of rows here, 6. We calculate our m control at the pretest, which is the mean of the baseline column. And then we calculate the standard deviation, which is the standard deviation of the baseline column. Then we do the same for the post well-being measure for mean and standard deviation. And again, we'll print these control descriptive statistics now. We have n control 6. We found m control to be an average of 3.833, and this is certainly something you can calculate yourself by doing 4 plus 2 plus 4 plus 4 plus 4 plus 5 all over 6. That should give you 3.83333. Then we also calculated our standard deviation for the pretest, and then our mean and standard deviation for the post-test and the control condition. Well, so we have all of the values we need to solve this problem. But since we're looking at whether the changes between two groups were different, we need to calculate just one extra value. So, or at least a couple extra values. So looking at the average change across time in the classical condition, we can just take our mean well-being at post-test and subtract our mean well-being at pre-test. We can also do the same for control. And we can calculate our standard deviation, our standard error for the change in classical and control. So from this, we figure out that the mean change in scores for classical participants was 1. And this is something we've already seen. We saw that they were at 4.5 at the pretest and 5.5 at the post-test. So the mean change in scores for those classical participants was 1. And then the mean change in the control condition was 0.3333, much less. We also found that the standard deviation of these changes were 0.48 and 0.51, respectively. Okay, so we'll compute the independent t-value now. Only this time, we're going to completely rely on R. We won't be calculating it by hand, but you're definitely free to use these values here to do so, and just to confirm that you get the same value. Again, we do the math here, and we assign it to this value t. And when we print t, we find out that the independent samples t-test is 2.335. So therefore, we find t equals 2.335 with df equals 6 minus 1 plus 6 minus 1 equals 10. Let's look this value up in the table. At 10 degrees of freedom, we find that we would need t equals 1.81 or more in order to observe a significant effect. So since our t is actually 2.335, that's much greater than the significant t we would need. So therefore, we reject the null hypothesis at the p less than 0.05 level. In other words, the change in well-being among classical participants was not due to maturation or history, because the null hypothesis was that the change in well-being among classical participants was due to maturation and/or history. So, therefore, we believe that the classical music intervention leads to an improvement in the well-being of Psych 292 students. Well, that pretty much concludes the tutorial for the day. This was a fun tutorial, but we've really only scratched the surface of what t-tests do and all of the statistical techniques that are available to you. We've also only scratched the surface of the R language, truly. We've only done some very basic manipulations. There are also many more analyses that we could run on these data, and I definitely encourage you to have a look at the spreadsheet and try some out for yourself, either by hand or using R. Ideally, I'm going to attach this very document in the video description, and I'll also set up a link to the actual code and spreadsheet with the data. So I hope you got something out of this. Thanks for joining me.